So sorry for the interruption for whole interruption. So let's start. This is tutorial 11, and obviously I will start with your problem. And obviously I have checked the whatever the problem assignment problem is there, those are very easy. So it does not, I mean, if we can do it in the last 40 minutes and 45 minutes around. Okay.
Obviously.
Yeah. So obviously I will not able to do full 2 hours, but I will go 8:20 up to at least. Yeah. I think recording is properly. Just so yeah, recording is properly. So everything is going properly. So this is tutorial 11. Advanced linear algebra. This is MSc 25 MA 03, and today is 5th April. So let's start some problem, and usual linear algebra problem. I don't know those problems are if those problems are okay. This is the problem, right? This is the problem for a variable different is okay. This is not a problem. So I hope problem is clearly visible now.
Yes, sir.
So this is one problem. So what it says, let for a variable x consider the R vector space, that is real vector space, v equals to a0 a1x plus a2 square, that is vector space of polynomials of degree less than equals to 2. This is the so that must be a vector space of dimension 3. So let T be a linear operator transformation that is given by this way. So T is the linear operator from V to V given by T of f is equals to f plus d of by dx, where df dx denotes the derivative of f with respect to x. Okay. So so which of the following statement is true? So yeah, obviously you can look at the thing is that there is some 2025, that's not a big deal, but let's find something. I mean, we have to do thing is that I have to find the characteristics polynomial. Matrix representation. So first you have to find matrix representation. So T will map 1 to 1 plus derivative with respect to that is 0, that is equals to 1. T will map x equals to so better to write first that 1x x square is an ordered basis. Note that 1x x square is an standard ordered basis. So therefore T of 1, that will be 1 obviously, plus 0, and T of x, that will be x plus derivative of that is 1, and T of x square, that will be x square plus twice x. So if we write it as, it will be 1.1 plus 0 dot x plus 0 dot x square, and this will be 1.1 plus 1 dot x plus 0 dot x square. This will be 0.1 plus 2 dot x plus 1 dot x square. So therefore matrix representation of T with respect to the above ordered basis is 1 0 0 1 1 0 0 2 1. This is the matrix. Yeah. So therefore, so if I write it as A, so let's then A minus lambda I will be 1 minus lambda 1 0 0.
So this is upper triangular matrix. So the
no, this characteristic is not. Characteristic polynomial is just product only, right?
Yes.
So therefore characteristics polynomial of A is equals to lambda minus 1 whole cube. This is the thing. So only thing is that, so minimal polynomial will be either, therefore minimal polynomial will be either
lambda 1 square or lambda 1 cube.
Yeah, that's true, because lambda minus 1 will not be, as one can write as as a is not equals to identity, that implies lambda minus
Yes.
1 is not the minimal polynomial. Minimal
Yes.
polynomial. So therefore one can directly do one thing, that let's write is a minus identity, then what is it is, it will be 0 1 0 0 0 2 0 0 0. So therefore a minus I whole square, that will be this matrix square, this will be first term will be 0, second term will be 0, third term will be 2, this will be 0 0, this 0, this is
Only
0,
one.
all will be 0. I think this is correct. So therefore this implies that one, I mean we can do more, and therefore it implies that a minus 3 identity, sorry, a minus I cube, that will be 0, right?
Yes.
A minus I whole cube will be 0, and one can check that this one with this first row, first column, zeros 0 0 0 0 0, yeah, that will be, there is no problem. So a minus I cube equals to 0. So therefore minimal polynomial is x minus or lambda minus, as I am writing lambda minus I cube. Therefore a minus I whole cube, or one can write it as like this way. What is the correct polynomial here? Polynomial will be lambda cube minus 3 lambda square plus 3 lambda plus 1. This is the minimal polynomial, right? I think minus 1 minimal polynomial, right? Minimal polynomial. Therefore what we can say is that a cube minus 3a square plus 3a is equals to identity. That implies whatever the power you can raise on this identity for all integer n, positive integer obviously, all positive integer. Negative integer is also identity, but here is negativity, we need to find what is the negativity, that means we need inverse and all those things. So for all positive n belongs to natural number, one can write, okay? So therefore n 2025 or anything, that doesn't matter. So therefore this is the polynomial. You can note that everywhere it is written this same way, right? So but the fact is that last term is something. So if you do a cube minus 3a square plus 3a, or one can write this is the, I mean now I can go back to the operator, right? T cube minus 3t square plus 3t, this whole cube whole to the power n is equals to identity. T will satisfy this equation because we are doing in standard order basis, so therefore there will not be any problem, okay? We are doing in standard order basis. If the basis is specified, in that situation we may have some different type of result, but as long as we have identity there will not be any problem, but still I am just saying. So therefore x at x will be at x, that is equals to x. So first option is the correct option. So obviously all other option will automatically be false. Is it okay?
Yes, correct.
And obviously this is not correct, this is also something similar, but this is not correct, right? Because we are getting t cube minus 3t square plus 3t equals to identity. So whatever power you raise, that doesn't matter, you will always get x, because that is identity, right? This is identity.
Yes.
So let's go to the second one. I think this is the second one. So what it says, let A be this matrix given and B be this matrix given. Which of the following statement is or are correct? Both A and B are diagonalizable over R. Okay, so first of all, A is not diagonalizable, B is also I think not diagonalizable. So, but let's check which of the following statement are correct. Both A and B are diagonalizable over R. A is diagonalizable over R but not over, also A is diagonalizable over C but not over R. Neither A nor B is diagonalizable over R, but both A and B are diagonalizable over C, and neither A and B are diagonalizable over C. Okay, so I think one can do easy tricks, but that will be little risky. That easy tricks is that you can multiply A with some invertible matrix P and P something this way, so to get the matrix like this one. Okay, I mean diagonal matrix, identity matrix. And this is the this matrix is actually a permutation matrix, right? This is permutation matrix. And what is
Yes,
the
sir.
permutation? You can directly, I mean this is some easy way. What is the permutation matrix? This is the permutation matrix corresponding to 1 goes to 2, 2 goes going to 3, 3 goes to 1. This is the permutation matrix. So this is 1. So permutation is 1, 2, 3. I'm going to in standard way, but this is the permutation. So this is the permutation means the degree of this permutation is 3, right? Because if you do 3 times, then it will get to the identity. So therefore a cube equals to identity. This is the correct minimal polynomial.
Yes.
I think this is the minimal polynomial, and this is the permutation matrix for a goes to 1 goes to 2, 2 goes to 3, 3 goes to 1. This is the permutation matrix. So therefore here will be a cube equals to identity. This is the thing. So but let's do the formal way. So therefore minimal polynomial is also in each situation minimal polynomial. This situation minimal polynomial is x cube minus 1 equals to 0. This situation is also minimal polynomial x cube minus 1 equals to 0. We know in both of these situation in real variable they don't have what is called
2 is correct, sir. 2 and 3.
A is diagonalizable over C, but not this is correct. Neither A or B diagonalizable over R, but both A and B diagonalizable over C. That's true. Neither A or B both A and B obviously over R तो diagonalizable है नहीं. This is not diagonalizable because x minus 1 and there will be degree 2 polynomial. But you understand this technique na, that permutation matrix. These are permutation matrix.
Yes,
let's
sir.
do for one.
Yes.
I can do through. I mean obviously you should not waste time in exam hall to doing all these things to check whether
Yes.
a cube will be identity or not. But this is permutation matrix and this is of degree 3 permutation. You will go there, and this is also degree 3 permutation, so you will go because you know that the next one will be 1 goes to 3, 3 goes to 2, and 2 goes to 2. When you multiply a, this is corresponding to a square, and the a cube will be 1 goes to 3, 3 goes to 2, this is 2, next one will be okay, sorry, I have written.
Sir, 1 goes to 1, sir.
3
1 goes to 1, 2
but
goes
I have
to 2,
written
3
1 goes to 3, 3 goes to 2, 2 goes to 1. So 1 3 3 2, but it will be a maximum 3 degrees possible. Just a minute. I understand. 1 goes to 2, 2 goes to 1. This will be 1 goes to 2. If you compose them, if you compose these two, a and a square, then you will get a cube, right? So you will get this one. Okay, but let's do it some little formally, because this permutation matrix, all this thing is not done, so I have to do little formally. So let's go there. That is the technique you have to use in exam, because you should not waste time there. So that is the technique. Okay, so these two will be correct, but let's check. A is equals to 0 0 1 1 0 0 1 0 0. I think this is the matrix. So a square will be 0, this will be 1, this will be 0, yeah, this will be 0, this will be 0, this will be 1, this will be 0, no, this will be 1, I think. Just a minute. This one with this 0, this first okay, let me write it clearly as I am doing. A square equals to 0 0 1 1 0 0 0 1 0 0 0 1 1 0 0 0 1 0. This will be 0 1 0. Next is 0
0 0 0 0 0 1.
1. Oh, last
No,
one
1.
is 1. Last one is 1. That's
Yes.
right. Last one is 1. Next one is 1 here.
1 0 0.
This is the thing, right? So you so now what we have to do is we have to multiply a and a square. That is will be 0 0 1 0 1 0 0 0 1 0 0 1 0 0 0 1 1 0 0. That will be 1 here. Just to verify, 0 0 0 here, 1 here, 0 here, 0 here,
0 0 1.
0 here, 1. This is identity, so clearly this, right? So therefore minimal polynomial polynomial of first matrix is x cube minus 1, right? Therefore it is the matrix, first matrix is not diagonalizable over R but diagonalizable over C, right? So I'll obviously not, you know, the what is called similarly the second matrix as minimal polynomial x2 minus 1, that implies it is not diagonalizable over R but diagonalizable over C, right? This is the correct one.
Yes,
So
sir.
I just, as a remark, I am writing it that one can do using the permutation matrix. What I just said first, one can do this problem using permutation matrix technique. Permutation matrix technique. So let's go to third problem. This is the third problem. So what it says, let M2R denote the R vector space of 2 by 2 matrices with real entries. R means real vector space. This is real vector space of 2 by 2 matrices with real entries. Let A is this matrix, B is this matrix. Define a linear transformation T by Tx equals to Ax B transpose. So where B transpose denote the transposition matrix, which of the following statement are correct? Determinant of T is equals to is 2 to 5. Okay, so therefore with respect to standard order basis, note that here we have, note that M2R have standard ordered,
Sir, we need to find, sir, matrix representation of T.
right? But that is, yeah, that's true, matrix representation over T, and that will be like something like, yeah, just let me, standard basis, I have to write the standard basis. So
Is
like,
there any other way, sir, shorter way, sir? Can I do, sir?
yeah,
So that can I do, sir. But is there any, sir,
short way,
shorter way, sir?
shorter way is
Yes.
that you have to do the determinant of A x B, because you know the matrix with respect to standard order basis. For example, you have to just for checking, if you take 1 0 0 0, this is the matrix, for example, then
Yes,
what
sir.
will be A transpose B? You will get A will be like 1 2 0 3, and with, just to, I mean, for assuring this one, I have to check once, this is 0, this
No,
is,
sir, transpose. So we
no,
need to
B
take.
transpose is there, I'm adding after that. So okay, just to check, when I'm checking I can do it in the side, below side, just one, yeah. I just want to say that will be determinant hopefully, but minus, I don't see any minus will be there. Determinant, product of product of determinant, I think that is what is possible, but I think determinant A will be twice and B will be twice, I think, or row of A B will be interchanged. So this is something general, but obviously I am not completely assured that how the determinant will be. Let's check. For example, if you have A matrix, so this is something like A11, A12, A21, A22, this is the matrix. Okay, now if you take the back, this is the first element, and multiply this, and this is, for example, B11, B12, B21, B22, right? This is the real matrix, so I don't take any conjugate anything, I am not taking anything, but this is the thing. Okay, so what will happen, A11, this will be A11, and next one will be 0, this will be A21, 0, and next one is B11, B21, B12, B22. So this will be A11, B11. Okay, I think this will be the tensor product actually. Just a minute. A11, B21, A21, B11, A21, B21. This is the thing, right?
Yes.
This is the thing. But now the basis you have to take something like this way, like 1 0 0. I hope this is the first one. You can take this is the first one. Second one is something like 0 1 0 0. Not this, not the other one. Like 0 1 0 0. This is the third one, and the fourth one is 0 0 0 1. I think if you take this, then you may get some pattern. So let's find it. Okay. So you may this in this particular you will find a pattern. That pattern. So therefore, what will be the matrix representation? Matrix representation will be like first term will be A11 B11 with respect to this basis E1 E2 E3 E4. Second term is A11 B21. Third term is A21 B11. Fourth term is A21 B21. This is the thing, right? So now if you just change one to here, because this is the standard basis I am taking. So what you will have, it will have this row will multiply, this will change only, this will be A11, this will be A12 12, next one is 0, A21 A22 0. So therefore this will be A12, this will be A12, this will be A22 22. Yeah, I have written correctly. So therefore this will be A12 B11, A12 B. Oh, I think
There should be A22 B11, na sir?
huh?
A22 B1. Second.
No, this one, this is correct. This is correct also, right?
This is correct, but in sir column, the matrix representation you are writing, sir, the element.
A22 B11, right.
And also, sir, this
This will also
A21 is also
interchange, right? This is also interchange,
yes,
right?
yes, sir.
This is will be A21 B11, and this is A11 B21. Yeah. So this is A22. So this is A22, and next is A12
A12
B21.
B21.
12 B21.
A22 B21.
A22 B21. Is there any pattern visible now? This is the thing. If you can take B11, you can take B11 common, right? Here, something like that. I just want to say.
And B21 is also there, sir.
That is what is there is a pattern. Okay, and if you go like this way, I am just obviously, but I know there is a pattern, but obviously I have to check properly. So if you just do here 0, so this will change. This will change like this one will be A first. Okay, first is 0, right? First element is 0. Second element is A11. Third element is 0. Fourth element will be A21, right?
Second row, second column will be, sir, I think.
Yeah, second column A11. Oh no, this also, this will change now. So what will be now? This will be A11 B12, and 0. Second one will be
A11 B22.
A11 B22, right? Third one will be
A21 B11.
B12, no?
B12. A21 B22.
So if you go that way, like A11 B12,
A21
A21 B12, and
A11 B22.
A11 B22, A21
A21
B22. Similarly, I hope you can write this way. Write B12 A22 B12, and here you can write A12 B22, I hope the next one will be like this way. Obviously,
Yes.
there must be
A
some
two
pattern.
two.
So this is the matrix. So you can look
Or
at
A
this
two
is
two.
called.
The last one A22, sir.
That's true. That's true. Thanks. So this will be something like A with multiply B11, A with multiply um,
B12.
B12. Here A with multiply B21,
B21.
A with multiply B22. This is the matrix, right? So
Yes, sir.
now you know that for determinant the block one is also going that way, I think. So you can write, I think, here determinant of A B11 square minus determinant of A. I mean this will be determinant of
So
S.
DT minus AD minus BC, sir, na?
No,
If
but this is matrix is there, right? Matrix is there. Not like that it will be. I think it will be determinant of A square, determinant of B square, I think.
sir, if the sir column, if the sir blocks in the first column, sir, commute, then the determinant will be, sir, AD minus BC, sir.
First
First entry in first column, sir. If commute, sir.
entry in
Then
first column, if commutes, then it will be determinant.
AD minus determinant of AD minus BC.
AD minus BC will be.
Sir.
I mean, if you have block matrix,
Sir. And first blocks in the first column, sir, commute. Then
okay,
determinant can be.
blocks in the first column, these two column commutes.
Yes, sir.
They are commuting here. There is no doubt about that, right? But still, I have little doubt. I think this is correct. That determinant of A square into determinant of B. I think this is the correct option. But why determinant of A square is happening? Because if we take transpose, all thing will be transpose. Yeah, I think determinant in that situation. Okay. I got it. This can be written as. This can be somehow written like common. This is something called A tensor product B. Usually it is called. Okay, just let me check what is the determinant of A tensor product B. This is what is called A tensor product B. Okay. Determinant tensor B. I think both of them will be power. Yes. This will be determinant. This is the tensor product. So here determinant will be the product actually. This is product square. Something like determinant of A square, determinant of B square. Actually, if A is an m by n matrix and B is an n by n matrix, so one can always define like this way: A with all entry of Bij, something like this way one can define a matrix. So for that matrix, determinant will be product determinant of A to the power m, determinant of B to the power m. Okay, so here it will be determinant will be this one. Okay, this is the, I mean, you have to check. That is, I don't believe there is obviously tensor product is there, but tensor product is not something. So here it will be, so this is one can formally can keep in mind that this will be determinant of A square, determinant of B square. If it is of 3 by 3 matrix, if A is 3 by 3 matrix, B is 3 by 3 matrix, then that will be a determinant of A cube, determinant of B cube. And if A is that way, if A is an m by m matrix and B is an n by n matrix, and for example X is something like sending m to n, right? T is the operator. T maps X to something like A X B transpose, where A is an m by n matrix and B is an n by n matrix. So X is must be needed m by n matrix. So X is mapping from m cross n to m cross n like this way. In that situation, So determinant of t with standard order basis, only with standard order, sorry, determinant will be always same, that doesn't matter standard order. Determinant of a will be determinant of a to the power m, determinant of b to the power m. Okay, this is the general formula, you can use them. So this is what is the determinant of a, that is 3, and determinant of b is -5. So 3 square into 5 square, that is equals to 15 square, that is equals to 225, and no minus. You can remember this thing, this is very interesting thing.
So this is kind of a tensor product, sir.
Yes, this is called tensor product actually. This is tensor product, I mean determinant of tensor product actually, and whatever the matrix representation, that is actually tensor product of a and b. But I
Yes, sir.
tensor
So
product
this is
yes.
yes, sir. And if A and B are 3 cross 3 matrices, then
Then into
we
power 3,
should take
even
cube, sir.
power 3, determinant of a to the power 3, determinant of b to the power 3.
Yes,
That's
sir.
why I am
Yes.
saying that.
Oops.
Let's T is the operator from space of matrix m by n to space of matrix m by n, and A is an m by m matrix, square matrix, and B is an n by n square matrix, and Tx is given by this way, Ax Bt, then it is well defined. Okay, in that situation determinant of T will be determinant of a to the power m, determinant of b to the power n. Here determinant of T means determinant of the matrix representation of T, but we know the matrix representation of a linear operator on a finite dimensional vector space, that is whatever it will be, but determinant will be same, whatever the order basis we may take, but determinant will be same always, right? Because that is the last term of the characteristics polynomial, so therefore that has to be same.
Yes, sir.
Okay, this is the thing, this is the another problem. So what it says, let for a variable x consider the real vector space, this is the thing, that means this is the vector space of degree less than equals to 3, so it has standard order basis 1x x square x cube, that is 4 dimensional. D be the differential operator, derivative of a with respect to x, and m be the linear transformation, that is something multiplication with derivative. Which of the following statement is true? So obviously, so here you can do find the matrix representation and check. Okay, so but we have to find the matrix representation, there is no other way, I think.
Yes, sir. Yes.
So matrix of D, okay, I think we have to find each of them. Let's by matrix of dm equals to md. So let's check dm. What is dm? M at the point 1, that is equals to, I mean whatever way you can take, it will be always long, it seems to me. So m at the point 1 is
D of
yes,
D of M1, sir.
yeah.
Okay, so you are checking option 1.
So d of f, for example, I'm just going to generally, okay. So mf is equals to d of x df, right? I can write this way. So that means first is derivative, we know this is the df, okay, plus x into d square f, double derivative. Okay.
Yes.
So
Yes.
therefore we know that d of x is always 1, so that is d of f always plus x into d square f. So here therefore, and what is the md? Md at f, what is that? That will be m into
Here means f dash.
that is d of f is equals to d of f I am writing, but what is m of something, that is equals to x into d of df, right? That is equals to x d square f. So therefore when d of f is not equals to 0, in that situation dm is not equals to md. You can look at these two terms, right? For example, one can take x, in that situation d of
So
x,
df is constant, sir.
no, that when it is constant then it will be equal, but that is not always true, na?
Yes, sir. Yes.
In that
Yes, sir.
situation,
If df is non-zero, then this will imply f is non-constant.
so this is the, so first
Yes.
option is, first option is correct, statement are true, so first option is correct.
Yes.
Now d and dm is invertible or not, so this option can be looking from this way. So let's take x is 1, okay, I mean f is 1, so first derivative with respect to a1, that is so dm of 1, that will be equals to
Zero.
0 plus
Zero, sir.
x into 1 a d square f, that is again 0, right? 0. So dm of x, that will be 1 and 0 because d square of x is 0. Now dm of x square, that is equals to twice x plus x because oh no sorry, x
Two
square
x.
2x,
Two.
right? That is
Only
4x,
two.
right? That is
Yes,
4x.
sir.
And now dm of x cube, that is equals to d of f a, d
X
of f is
plus
equals to 3x square plus x into
plus six x
6x square, right? This one. So 9x square, right?
nine.
Yeah. So therefore matrix representation will be 0 0 0 and 1 0 0 0. The fourth one will be, if I take 1 x square x cube is the ordered basis with respect to
Yes,
that.
sir. Yes, sir. Yes.
So this is 4, this is
The
0
zero
and
four.
huh. So 9 0, right? This is the thing. So therefore this is a nilpotent matrix, clear? Not diagonalizable.
Yes. Yes, sir.
I think no explanation is needed here because this is nilpotent matrix which is not 0. So therefore this is not diagonalizable.
Non-zero.
Hmm. So dm, oh sorry, dm is invertible, that is false also. Not diagonalizability, that's invertibility. It is false. Correct?
Hmm. Correct.
Huh. So now what is d plus m? So d plus m at some f, what it is giving? D of f plus mf. But what we know, mf
X D F.
mf is x of df, right? So
X D
therefore
F.
this is equals to 1 plus x into df. Okay, so let's again do same thing. I hope this is not correct. So this is 0,
So this can we write as D of X F.
d of,
X F, sir. Derivative of x into f.
oh this one, ha, derivative of x into f. But okay, that is okay, same thing we have to find actually. X, that will be 1 plus x, this is only d plus m into x square, that is equals to 2x 1 plus x, that is equals to 2x plus 2x square, and d plus m x cube, that is equals to 1
3x.
plus x into 6x, right? 6x square, sorry, not 3x square,
6x.
no no,
So
3
3x. Sir.
3x square. So 3x square plus 3x
Plus
cube.
3x cube.
So therefore matrix representation will be 0 0 0 0 1 1 0 0. Other will be 0 2 2 0 and 0 0 3 0. Sorry, 3. Right? This is the matrix representation. 0 3.
Yes, sir.
So
Not invertible. Huh?
now
No. We cannot say. Yes.
now we can't say. But what we can say is that the
Determinant 0, sir.
diagonal entries are the eigenvalue, na? So why you can't say anything? So therefore one of the eigenvalue of the
Determinant
matrix
is
0.
0, sir. No?
Huh?
Determinant is 0, sir. Not invertible, sir.
The eigenvalue is 0, so not invertible.
Or sir, one sir, row is one column is 0, sir.
Determinant is
Then
0, whatever you say, determinant is 0. So therefore this is invertible, that is also false, right? This is also false. dm is invertible, that is also false. Rank of dm and md. So one can look at what is the
sir,
rank
I
of
can say
dm is, that will also be false, but let's check. Note that rank of dm is equals to, that was dm, right? Yeah, rank of dm is equals to 3 because 3 non-zero row is there and that is not possible to reduce. Okay, and what is md of f? That is equals to m of df, and that is already we written that one. That is equals to x square, x of d, md is equals to x of d square f, right?
sir, MD of sir 1 was 0, na sir. MD of 1 was 0, so kernel is non-zero, sir. So
No, 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 but
MD is
here it
not
is asked that not invertibility. Here is the rank of dm equals to md or not. Both rank is equal or not.
no, no, sir. I am telling that rank is sir 3, sir.
Yes, but it can be 4,
DM
no?
rank of DM is. Ah, sir. Yes, sir. Yes, sir.
Got it? It is a 4 by 4 matrix, not 3. Rank
Yes, sir.
dm1
Yes, sir.
is
Yes, sir.
equals to 0. D, still you are correct, this is not x, this is 0. So that is giving the rank
Ah,
will
sir.
be,
Now we Yes, sir.
So
Be less than
mdx square is equals to, it will be 2x, and mdx cube, that will be 6x square, right? So the matrix will be 0 0 0 0 0 0 0 0 2 0 0
sir.
0
Range have sir two linearly independent vectors, so
0.
rank will be sir two.
So rank is 2, so therefore rank of dm is not equals to rank of md, so therefore this is also false.
Yes, sir.
I think this is the next one. What it says, for a 4 by 4 positive definite real symmetric matrix A, real numbers a b c d, consider the 5 by 5 matrix this. 4 by positive, A is a 4 by 4 positive real symmetric matrix. Okay, then the following statement are necessarily true or not. Actually I am not supposed to do this, still I am doing this,
Yes, sir.
because
Yes, sir.
this can be done through the this
Sir, this is in next lecture, sir.
huh?
This, sir, this is in next lecture, I think,
Yeah,
sir.
that quadratic equation one can do.
Yes, sir. Yes,
So
sir. You can skip it, sir.
okay, so let it keep, let's keep it. Oh, this is the thing. Yeah, I think this is good question. I think let's do it. This will may take little time, but this is, I don't know whether real analysis, how much real analysis will be involved. Span of the real vector space of continuous function, both v and w are infinite dimensional. Let's do it, check. What it says, let u denote the span of et e to the power t 2t e to the power 3t in the real vector space of continuous functions from R to R. Consider the real vector space V, that is all functions which is an R linear transformation. Okay, these are the linear transformation. V is taking set of all linear transformations. So you can note that this is a linear functional on U. U is a span subvector space, okay, of vector space of continuous functions, subspace of continuous functions from R to R, and W is something which is making 0 at the of all those f in V. So here let V dash is equals to space of all real valued continuous functions on R. Real valued continuous function on R. Okay, so V is basically subset of V dash and W is subset of V. Okay, so which of the following statement is true? Both V and W are infinite dimensional. Okay, both V and W are infinite dimensional. Oh, V is just vector space. Okay, dimension of V is 3,
Sir,
dimension of
if we are able to sir find the dimension of U, then we will also find the dimension of V because
that is the finite dimensional and the dual, that is actually.
yes, sir, dual.
So what is the dimension of vector space? So if so V, we know V is equals to, given that will be 3. Let's check this one. Given that V is equals to span, or I can write
U,
span.
sir, U is equal to sir.
Sorry, U is equals to not V. U is equals to span e to the power t, e to the power 2t, e to the power 3t, right? Right?
Yes, sir.
Okay. So whether they are linearly independent or no, that is the question.
They are always linearly independent. So
They are linearly independent, but we have to prove that they are linearly independent. So therefore the basis will be dimension 3, linearly independent. Why that is? That is the only thing.
by finding Wronskian, sir.
Finding?
Wronskian, sir. Wronskian of
Yeah,
sir.
but I will not be able to use the Wronskian. That's, I mean, obviously I will not be able to use Wronskian. That I understand, but I have to think little differently. I got an idea. Let's check. So let
Sir, by taking the t is equal to 0 and
let's
differentiating.
consider, let ft equals to e to the power a ft, b e to the power 2t plus c e to the power 3t. If ft is equals to 0 for all t belongs to real number, we if to show that e to the power t, e to the power 2t, e to the power 3t are linearly independent enough to show that if t equals to 0 for all t belongs to R implies that a equals to 0 equals to b equals to c, right? So what is the f dash t? That is equals to a e to the power 2t, a to the power t, a e to the power t plus 2b e to the power 2t plus 3c e to the power 2t. Now f dashed double dashed t, that is equals to a e to the power t plus 4b e to the power 2t plus 9c
Plus 9 yes sir.
3t.
Now put t is equal to 0.
Yeah. Now let take, I have to show that this is, I mean if f is equals to 0 for all this, if f t equals to 0 for all t belongs to R, that implies f dashed t equals to f double dashed t equals to 0 equals to f t for all t belongs to R. That should happen, right? Because
Yes
f
sir.
is 0 function there, right? So therefore
Yes.
what will have a e to the power t, 2b e to the power, okay, starting from this, b e to the power 2t plus c e to the power 3t equals to 0, a e to the power t plus 2b e to the power 2t plus 3c e to the power 2t equals to 0, 3t, a e to the power t plus 4b e to the power 2t plus 9c to the power 3t equals to 0. And you know this will give a b c, a 2b 3c, a 4b 9c, right? E to the power t, e to the power 2t, e to the power 3t, this is equals to 0, and that will only happen whenever this matrix, determinant of this matrix, okay, if this is 0, then we must have determinant of this matrix is 0. Why this is? Because why in particular one can take, I think there is, okay,
Sir,
sorry,
why you
I understand.
not put sir t equal
Got it, thanks, yeah. Why I have to
sir,
replace
because
t
it
equals
is
to
t
0,
for all t.
right, I have
Yes
to
sir.
replace t equals to 0, that's all. Yeah, that is the Wronski and go actually. Take t equals to 0, then a plus b plus c equals to 0, a plus 2b plus 3c equals to 0, a plus 4b plus 9c equals to 0, and this is what it is saying, that 1 1 1 1 2 3 1 4 9 abc 0. So this will be 0 if determinant of this matrix, this will be 0 if determinant of this matrix is determinant of this matrix is non-zero, right? If let a equals to this matrix 1 1 1 1 2 3 1 4 9. So now what is the determinant of a? So that will be non-zero, because you can look at that, none of the rows are actually they are linearly independent. You can check this is because they are linearly independent. You can, this is not equals to 0 because this is 1 1 1. If you subtract it, so there will be something always, okay? So therefore what will have, a equals to b equals to c equals to 0, and this gives that e to the power t, e to the power 2t, e to the power 3t is linearly independent. Okay, this is linearly independent. So that says that the vector space V is of dimension 3, and so that says that W is already dimension 1, because you know that okay, no, W is dimension 2, I think this is false, sorry, dimension 3. Both V and W are finite dimensional, this is false. V is infinite dimensional, that is also false. So obviously these two up, obviously 3 will be, last option will be correct. So let's just quickly check. Dimension of W is 2, because why dimension of W is 2? because you know that um, all those functions which annihilates the last term, that will be the okay, just let me go to what is the w. It is given w is equals to all those functions f belongs to v u v such that f of e to the power 3t equals to 0. So that means we have a order basis. Yeah, we have an ordered basis. For example, if you just I will not go to detail explanation, just recall the some vector space. Suppose we have an ordered basis alpha 1, alpha 2, alpha n, and corresponding to this order basis I am going to discuss what is the v star, that is equals to alpha 1 dash alpha n dash or f1 f2 fn, f1 dash all the way fn dash, right? So now if you know that this fi vector fi is something, sorry, not dash, dash is not needed, this fi is a vector which says something like fi alpha j is equals to delta ij, right?
Yes, sir. If I is equal to j, then this is 1. If I is not equal to j,
So
then 0.
therefore it is annihilating, I mean therefore what are the number of fi is there for which a particular alpha will be 0, that is obviously n minus 1, right?
Particular alpha will be 0.
Yes, because for example I am taking alpha 1, what are the f
Ah, sir,
there
yes, sir. Yes,
for
sir.
which alpha 1 will be 0, that is up to except first one, all of them n minus 1.
Sir, if alpha 1 is e to the power 3t, then that will be non-zero, sir.
Yeah, I'm just saying that there is an obviously they are or the standard order basis, right? They are linearly independent standard order basis, and this business is for linearly independent standard order basis. Sorry, not standard order basis, for linearly independent basis, ordered basis. I need an ordered basis, right?
Yes, sir.
If I have an ordered basis, I can create the dual in such a way that fi of alpha j will be delta ij, right?
Yes, yes, sir.
So that way this will be, you understand this n minus 1 will be the thing. I don't know who joined, maybe what is his expectation, he just leave now.
Yes, sir. He has left.
Yeah, but he may have some expectation, I don't know. That is 2 is clear, right? There is no explanation, I
Is there
say.
any, sir, analytical ways, sir? Let's say we are able to prove that there are only two linearly independent vectors in sir W.
E- yeah, there is only 2 linearly independent vectors. That way I think there will be some little problem. I don't know, I am not seeing right now any other technique to say that W has dimension 2 except this dual thing.
Sir, we can form the basis of sir V, sir.
Yeah, that way I'm saying this alpha
And,
1, alpha 2, alpha 3 are
uh,
bases, right?
uh,
So
sir.
now corresponding to this it will have 3 dual, its dual will have 3
Three.
element, 3
Yes, sir.
element. If you
Correct.
note that what are the dual element, that is f1 is something which makes alpha, f1 is something which makes alpha 2 0 and f of alpha 3 0, but f of alpha 1 need not be 0, right? And
Okay, sir. So, sir, second, the last term will be sir 0, sir.
yeah, you know that f3 will be something which
Ah,
makes alpha 1 alpha 2 0, not alpha 3 0. So f1 and f2 they are making alpha 3 0, right?
ah.
Got it? And they are linearly independent.
Sir, if we take sir alpha 3 as e to the power 3t, sir. Sir, listen to me, sir.
That was I am taking. Obviously alpha is 3, I am talking about this one.
Alpha 3 is
E
e
to
to
the
the
power
power
t,
3t.
e to the power 2t, e to the power 3. They are linearly independent ordered basis. There is no point about that.
Uh,
And we have, this is v. So v star is equals to, there will
F1.
be f1, f2, f3. How this is things? This is span obviously. So how
Ah,
this thing is, f1 will make e to the power t 1 and all
ah,
other e to the power 2t
0.
equals to 0, and
Ah,
f1 will make e to the power 3t is equals to 0.
yes,
Similarly f2 will make e to the power t equals to 0, f2
correct.
e to the power 2t not equals to 0, that is
Ah,
1 actually, that is
1.
1, and f2 e to the power 3t is equals to 0.
0.
Similarly f3 will be something which makes e to the power 3t 1 and all other 0, right? So
But
therefore,
it is given, sir. But it is given that e to the power 3t 0, sir.
yeah, so that means f2 or f1 will be there, na?
Ah, sir.
So therefore
F3
dimension
will
is
be
2 and they are
also.
linearly independent also.
Yes, sir.
Huh. So this is the
So F3
dimension.
will not F3 will not be there.
F3 will not be, F1 and F2 is the candidate. So therefore this is the
Sir,
correct
but
option. Yes,
sir,
yes,
in
yes, yes.
this way, we should define in this way the dual basis for sir. If EIs are sir the standard order basis, sir, then we define this, sir.
No, no, no. Standard ordered basis, no needed.
You can take any sir linearly independent
Just
vector.
linearly independent is enough. Ordered basis. I need an ordered basis.
These are ordered.
Yeah.
Okay,
So
sir.
yeah, you can give order. Na this one
Yeah.
big power is
Yes.
order. Order basis I can give order always.
Correct.
And
Yes.
whenever you have finite basis, you can give always order. That is not a problem.
Okay.
Okay.
Yes.
So
Clear, sir.
so this is total class is of now 55 minutes. So obviously I can do more 20 minutes of this problem, and after that I have to go there a little bit. I think this is, let's do this one. So screen is visible, right? No problem is there, or no problem is, some problem is there?
No problem.
Oh, the new problem is visible, right?
Yes, sir.
Okay, there must be some network issue right now. I don't know. Maybe it seems to me that there must
No,
be.
no, sir. It is visual, sir. No problem, sir.
Okay, so let V be the, what is this? Is not the, okay. This is, I think, not quadratic equation. Let V be ABC R cube B R3 be a non-zero vector that lies in orthogonal complement of the row space of the matrix. This one. That means here, whenever you don't have, oh, there it is written that standard inner product. It is written standard inner product. So we know that what is the standard inner product of R3. That is x and y inner product is equals to summation of xi yi, because here it is the standard inner product 1 2 3. We have three things. So what it is saying is that let V be the ABC non-zero vector that lies in the orthogonal complement of the row space of the matrix, this row space of this matrix. That means the row that is generated by this row. So what is the smallest possible value of mod A, B and C? So that means we have to find a vector A, B and C, and you know that these two are linearly independent, right? These two rows are linearly independent because one of them is not linear combination of other, right? So
Correct.
one is linearly independent to other. So obviously there is an ABC, I mean, and there is total space is R3. So in orthogonal complement there will be only one dimensional space. There will be one vector.
Yes.
So that means there will be a smallest one with which we can multiply anything, right? So that is what we have to find. And you know this is very easy thing, but let's do. So if let's, so formally if I just start writing ABC, this is the vector in R3 is in orthogonal complement of 2 2 7 3 1 4. Okay, this span, I have to write span of this, complement of span of this, right? So that means 2a plus 2b plus 7c, that is equals to 0. 3a plus b plus 7c, that is, sorry, 4c that is equals to 0. That gives basically a plus b plus, sorry, not a plus b plus c 0. I think you can do many things here. From where one can start, but you can do many things. Let's do the usual, because we have two equation only. So multiply this equation with 2, that will be this will be 2a plus 2b plus 7c equals to 0, and this will be 6a plus 2b plus 8c is equals to 0. So if we subtract, let's write it as 1 and let's write it as 2, and so 2 minus, I mean there must be some formula if you have more equation, but here it is smallest equation, 2 equation is there, so I am doing usual 12 standard. So this will be 4a plus c equals to 0. You know that if I multiply, subtract 1 from 2, then it will have this one, 4a plus c is equals to 0. That implies that c is equals to minus 4a. Now if I replace c equals to minus 4a, c equals to minus 4a in where I should replace, any place one can replace, in 1.
We need to find sir B also na, in terms of sir A.
I am going to find, that will be here, na? So c, this will be minus 28. minus 28c equals to 28a equals to 0, right? So therefore what I am getting, 2b equals to 26a, that means um, b is equals to 13a.
13.
So therefore here it is asked what is the mod of ABC. Okay, so what one can write here is the term is that, so therefore a b c is always something, one can write it as 1, b is 13 minus 4, right?
Yes, sir.
So
So this
therefore,
is actually, sir, this is the actually basis element, sir,
yes,
for
this is
the
the basis
complement.
element. So you know that total mod of a blah blah, if I take this is ABC, then total mod of ABC is equals to what is that, 1 plus 13 minus 4, that is 12 minus 14 minus 4, 10, right? Now if I even multi a, if I take what is the smallest, here it is asked a is in R3, so I think there must be, says they must all integer, obviously they needs to be all integer, otherwise I can make this is infinitesimal small. So if ABC all are integer, so as 1 is there, I can't take any integer common, right?
Yes, sir.
So therefore either it will be this one or multiplication of that if I want to get integer, right? I mean there is no smallest combination of integers, because one of the element is 1, so I can't take any integer common. So therefore either it will be this is or anything integer multiple of this, because if I multiply non-integer, 1 will no longer be an integer, I mean after multiplication with 1. So therefore this is the thing happening here, but if we multiply any integer, that is add is plus or minus whatever, the mod value will be scalar multiple of 10, right? So therefore that will be increase, it is always, so therefore this is the only option. I hope this is clear now.
Sir,
Yeah.
sir, how can we prove this is the smallest by any analytical method, sir?
Yeah, don't go this analytical method. Here it is given three things. One is the ABC all are integers, right? Okay, so we
Yes,
have the
sir.
thing is that it is multiple of 1, 13 minus 4. So what are the solution is possible? All scalar multiple of a, right? Now if I want to get a 13a minus 4 integer, at least a should be integer, all of them is integer, at least a should be integer. So whatever the sum will be, for example this is the thing, whatever sum will be, that will be 10a, right? Always 10a, and the mod of 10a. So whatever a I may take, that will be 10 into mod a. So now say me that what is the smallest possible value of this by taking a is integer. You
Here
can
we
take
can
0,
take one.
but 0 is
One.
not the option, right?
Uh,
We have to take 1 or minus 1. This is the only option.
I think they are given non-zero integers, I think.
Obviously non-zero, because we are non-zero, yeah, non-zero vector. Non-zero vector is given. So therefore there is no other option. I have to take either a is minus 1 or a is plus 1, right?
Yes, sir.
So therefore, or therefore this is the only option. Clear, I hope, right? It's clear,
Clear, sir.
right?
Yes, sir, right.
I think this is the. So let V be the R vector space of 5 by 5 matrices. This is very good problem. This is very good problem, I think. Let V be the real vector space of 5 by 5 matrices. S be the set of all commutator AB minus BA. AB is coming from V, and W denote the subspace of V spanned by S. W denote the subspace of V spanned by S. So that means this is the commutator space. Okay. Let T from V to R be the linear transformation mapping a matrix A to its trace. Oh, this is easy then when it is matrix. So T is the operator from V is the space of all M by N matrix. So V is the space of all 5 by 5 matrix over R. So V is the space of all 5 by 5 matrix over R. So what it is says that T is the linear operator from, okay, S is, I will write S. S is equals to all AB minus BA such that AB belongs to V. So now T is the operator from V to R what it says, T of some operator A is equals to trace of A. Okay, then which of the following statement is true? So what is the important interesting thing here is that this is a T is a linear functional, right? Okay, and a dimension of V is equals to 25 over R. Okay, so that implies that dimension of kernel of T, that is nullity of T, that will be 24. You know the rank of the linear functional is always 1, so therefore rank nullity theorem will give the dimension of kernel is n minus 1.
Yes, sir.
So 24. So what I have to left is that if I can show that S is the kernel of the operator T, actually functional, then we can say that the dimension of the W and okay, S is the set, W is actually span of, okay, W is span of S. We can write like this way, AB minus BA such that A and B belongs to V. So if I can show that this W is actually the kernel, exactly the kernel, then or W is in the kernel. Okay, W is exactly kernel. Oh,
Kernel of what, sir?
sorry. We don't need to go to dimension actually. You can directly say, okay, if W is in kernel, okay, I have to check whether W is in kernel or not. That is what is the only fact, and it is exactly or not. That is what. So clearly, if AB minus BA is in W some element, then trace of or T of AB minus BA, that is equals to trace of AB
0.
minus BA, that is equals to 0, as it is known that trace of AB is equals to trace of BA, and we know that T is a linear function. So I can first split into linear and then I can use the fact that this is. So therefore that
So, sir,
implies,
T you have taken as trace of A, sir. T
yes.
is equal to A is equal to T. Okay, sir.
So this is the thing, this is the operator now, AB minus
Okay,
BA.
sir.
I have to first break it, AB trace of AB minus trace of BA, then we have to use this. So W is inside the kernel. So whether it is proper or not, all this thing is there. So these two are something nonsense because W is in there, so we don't need to go intersection and all these things. These two are, I think, not necessary, but yeah, one of them will be correct, but that is will be decided if we can say that whether it is proper or exact, right? So now if we can show that what is the dimension of the space of W, yeah, dimension of the space of W is, note that if an element, or I can write it as some other vector matrix, what will be the other P, if P is in W, then diagonal entries of P are 0. You know why this is things, because P is equals to AB minus BA, right? So therefore P II entry, that will be AB II, that means diagonal, minus BA II, that means summation of AIK BKI, K equals to 1 to R, minus summation of J equals to 1 to, sorry, not R, what is that, this is 5 here, 5, this 5 is something not usable, AIJ BJI, because here is no, this is just usual product, right?
Yes.
Diagonal entries will be same, so that is 0, so that means each diagonal entry is 0. Therefore it is saying that dimension of dimension of W is must be less than is equals to 25 minus 5, because diagonal entries are 0.
Yes, sir.
That is equals to 20, but but we know dimension of kernel of T, that is exactly 24. That is exactly 24. Therefore, W must be subspace of proper subspace of kernel of T. Is it clear now?
Sir. Sir, W is subspace of kernel of T, sir.
But whether it is proper or not, W is subspace of kernel of T, but this is proper, right?
Yes, sir.
So therefore, this gives first option is false because W is equal to kernel T. Second option is correct, but as well as it is saying that W intersection kernel T, that is exactly equals to W, right? Because W is subspace of kernel T, right? So
Yes, sir.
this is correct then. This is actually saying same thing, but then this is not correct. W intersection kernel T, which is W, that is proper subspace of W, that is false, right?
Sir.
So 1 and 3 is false, but here it is which of the following statement is correct. Why this is the following is correct? Because one is clear that W is subspace of kernel of T, that is clear. I think this is something, because it's clear that whenever W is subspace of kernel of T, if this is true, then this has to be true. I mean, what two option will be correct always?
Sir, I think this is correct question.
Huh?
Sir, MSQ type question. I think
No, but
this
it is
will be,
saying
sir.
is, that's why I am saying. Which of the following statement is true? I think this is
Statements
what
is true, sir. Statements. Sir, statements, sir. He is saying that statements.
Statements. Yeah, this is grammar.
Yes.
Okay, sorry. I hope this is correct. If you can check, you can check. But this is, I think, this two option is the correct. And here always two option will be correct because this W is kernel of subspace of kernel T. That is too much true here. So there is no other option then.
Yes.
So let's do. We have done this one now. I think we have done this one. No, we have not done this
No,
one,
sir.
but this is something, the same equation I have taken.
Yes, sir. Yes, sir. Yes.
So for a variable x, consider the Q vector space that is rational. That is extra thing. It is asking A, B, C, D all are coming from rational. Further, let A is the set all those field. Here field is the Q. F is Q linear transformation, that is linear functional. B is something which maps 1 to 0. That means, oh, this is same way. Which of the following statement are true? So you can check here whether multiple option is possible, correct or not, because it seems to me that multiple option is correct. Because whenever you have W is subspace of kernel T and we are getting W is proper subspace of kernel of T, W is not complete subspace of kernel of T, right? Because W will be subspace of real vector space of R by R matrix, but the diagonal entries of W will be 0 because those are actually linear span of AB minus BA, and AB minus BA has diagonal entry 0. So therefore W is subspace of kernel of T. There is no doubt about this because we have given 5 by 5 matrix. So therefore it will have some, I mean, dimension will be at least 5 reduced. So that means at least at max it will be 20 dimension of W, and kernel of T dimension is already 24. So please check this one whether this is multiple option is correct or not for this question.
Yes.
Okay, so for this one, this is R written, so that's why I just concerned. Okay, so yeah, this is this type of questions. So we have done it for the e to the power t, e to the power 2t, e to the power 3t. That is the same questions here, but in different language. Here it is written that f is q linear transformation, and b is something f making 1 0. So let's take 1 x square x cube. This is also standard order basis. Is a standard order basis of V, right? So A is giving, so that means the dimension of V is equals to 4, and A is the collection of all linear functional.
This is also 4.
Right, all linear
and then dimension of B will be 3.
That implies, I hope so, dimension of A is equals to 4, and B is given as the all those f belongs to A such that f of 1 equals to 0. That implies dimension
Yes.
of B is equals to
B is
3.
equal to 3.
R2, dimension of B is equals to 3, that's true. If f belongs to V, dimension of kernel of f is equals to 3, that is also true. You know, because f is a linear functional. Whenever f is a linear functional,
Sir.
kernel will be always dimension 3 because total dimension is 4.
Non-zero linear functions.
Yeah, non-zero. Obviously, f is non-zero. Okay, f is, yeah, no. That's true. F actually elements in A. Yeah, I think this is the something about the statement. In general, when you take no. A is the set of all linear transformation. Non-zero is not said anywhere. So if we take non-zero, then it will be 3, otherwise not. That's the problem.
So
Whatever,
we cannot choose option 1.
then we can't choose option 1 because we can take
Yes.
0, because here it is, I think none of the place, neither A is said as the set of all non-zero linear functionals, neither B is said as the non-zero collection. So
Yes,
dimension
sir.
of A is 4, that's true. That is
True.
true, right? Dimension of A is 4, that's true. If A belongs to A, then the image of A is one dimensional Q
Yes,
vector
sir.
space.
Correct.
That is also true because this is actually exactly full Q.
Sir, if F is sir non-zero, sir.
Yeah, again F is non-zero.
Yes, sir.
F is non-zero. Yeah, when F is non-zero. So this depends on the either 1, 2, 3 is the correct option, or 1, 2, 3, 4 is the correct option. Maybe
Yes,
this
sir.
is this some mistake is there. Maybe as I can understand that this is
This
not
is
the
sir, very,
this
yes,
is
sir, very
not
minute mistake, sir.
this is not net question. I can understand that. This is some sample questions.
But this is net question, sir. All are sir.
All are net questions.
December 2024, sir.
Oh, so that I mean those type of problem is, I mean, going to like drop, either they drop those questions or sometimes they can take, I mean one can challenge those questions that 0 is there if 1, 2, 3, 4 is the option,
Yes.
because in that way as it is not writing anything, so one can take 0 because A always contains the 0 1, right? Linear function of
Yes, sir.
everything is there,
So
one can take 0.
this is not always true, na, sir.
Yeah,
Why can
so
anyone,
that
sir,
means it's obviously they are not don't want to take 0 is the option, they have made mistake, that is clear. Okay, so what it is said that A, B, C are real numbers with A dot B dot A product of A, B, C is 1, B is equals to A plus A square plus A cube, then which of the following statement is true? So obviously after making A cube will be 0, I hope.
Yes, sir. No, sir. There is C also, sir. In last.
Oh, there is C, sorry.
uh,
So that's why, okay. 0 A 0 0 0 B C 0 0. This is the ABC, right? Now this is the matrix. Now B is equals to A plus, then which of the following statement is determinant of B is equals to okay, let's do whatever, let's multiply first. I hope that will give, I mean there must be some easy trick, but as this is smaller matrix you can do directly also. This is smaller matrix and there is entries are very small, entries are very less, actually 3 entries is there, so most of the term will be 0. I hope this is 0, this is 0, this is AB, this is BC, this is 0, this is 0, this is 0, this is AC, this is 0, I think. Right, this is the ABC. Okay,
So that
okay, now you have to make A cube. A cube will be interesting, I think. A cube equals to 0 A 0 0, I think there you will have ABC, I hope. 0 0 B C 0 0. If you multiply 0 0 AB BC 0 0 0 AC 0, so what it will be, you can look at this first term is ABC, second term is 0, third term is 0, this is 0, this is ABC, this is 0, so there is no easiest way. as it is given ABC, we have to multiply. That's the only way.
Yes.
So as we know that this is equals to 1 0 0 0 1 0 0 0 1. So you get that a cube equals to identity. So minimal polynomial.
ABC is also there, sir.
Huh?
ABC times identity is na, sir.
There is no C. It is written that ABC equals to 1.
Where?
Within question it is
Ah,
given.
yes, sir. Yes, sir. Yes.
Oh, so that's what I have to write then, as A B C is equals to 1. So if you want to use this one, you have to multiply this one. There is no other. I don't say any other way. Okay, so this is as well as minimal polynomial and characteristics polynomial also, because this is 3 by 3 matrix, so there will not be more than this. So which of the following statements? So therefore what we got, a cube is equals to identity, this is the thing, and b is written as a plus a square plus a cube. B is equals to a plus a square plus a cube, that is equals to identity, plus a is 0 a 0 0 0 b c 0
B will
0.
be 0, sir. I think.
No, there is no relation with ABC. There is no relation with ABC. Only the relation is that ABC equals to 1.
We take, sir, A common, sir. Then we can write B is
What?
equal
Okay.
to A.
Sorry, I can't. Yeah.
Sir, if we take A common, sir, we can write it's A times I plus A square.
That you can write. Yeah.
And
But that
A
is
cube
not.
minus I is.
No. Here you know that there we have the factor. That is a factor only. This is a factor, right? This is not necessarily
Yes, sir.
0.
Yes, sir.
This is not necessarily 0.
Yes, sir.
Because we have
Yes,
seen
sir.
that x square is not getting 0. X square is not able to get some way. This is the minimal polynomial. This is the minimal polynomial, and
Yes,
this is the characteristic polynomial. So those will not be making 0. I mean lower will not be. So we have to write the second term, that is 0 0 AB 0 0 AB BC 0 0 BC 0 0 0 AC, I think. Yeah, this is the identity plus a plus, this is a cube is the identity, so this is the thing. So what one can write is that, I think one can write it as
Sir,
a cube equals to, yes.
sir, to find determinant B, sir. Sir, we can find the
Oh, we have to
eigenvalues
find
of
rank
B.
of, yeah, right. We have to find rank of B. Yeah, that's exactly. Thanks. This is exactly, yeah. So what are the eigenvalue? Eigenvalue is we don't need to go anything. Yeah, right. That's true. So
ABC plus ABC square plus ABC cube.
therefore eigen values of A are 1 omega square, where omega is
Yes.
1 minus plus, what is the minus b plus minus root under b square minus 4ac. This
3 by
will
2,
be
the
1
minus
plus
1
3 by
plus
2 I
5.
by 2. I think this is, I think minus plus doesn't matter. Initial one is minus or plus.
Yes.
A square minus x. No, I think this is a
I
minus
think
1.
minus 2.
Minus
Yes.
1 is there, right? This is the correct one. In between minus plus can be changed, but minus 1 is, I think this is correct. Cubic root of 1. Cubic root of 1. So therefore eigen values of B is equals to 1 plus 1 plus 1 comma w plus w square plus w cube comma w square plus w to the power 4 comma
So all will be 0, sir.
No, first one is there, na?
Yes, sir.
6. So this is 3, and this is obviously saying that 1 plus w square, that is 0, and this is obviously saying that w square
Same
plus no w plus this is 1. That's the same thing. That's true. That's same thing. So this is equals to 3 comma 0 comma 0. These are the eigenvalues. So obviously determinant of which of the following statement is true? Determinant of B is 1, that obviously false, because B is 0, because one of the eigenvalue is 0. Determinant of A is 0, that is not sure, because A B C need not be Obviously A is non-zero because A cube equals to identity. If A cube equals to identity, why ABC determinant of A will be 0? That is
Yes,
not
sir.
true. Rank of B is
So
2, that is
fourth is
also false. Rank of B square is equals to 1, that's true. This is
no,
only
sir.
This is only true.
Rank of B is equal to 2 is false.
Because we have 3 eigenvalue 3 0 0. So if you write the matrix Jordan canonical form, that will be 3 0 0, right? There must be, oh no, rank of 3, that's true, sorry, there I have to do something, sorry, this is not correct. So this is, sorry, this is not, this is rank of B is 2 or not, that's the thing, right? How to say rank of B is 2 or not? Why rank of B is 2 or not? Okay, I think, I don't know whether I have to go to back to the scroll thing or not. Rank of A, yeah, it has eigenvalues 300, that's true, but yeah, oh no,
So this will imply the rank will be strictly less than 3.
strictly less than 3, either 2 or 1, that's true, but why it is not 2?
Hmm. Yes.
Yeah, if one writes this way, the matrix is something like 3,
Sir, 0 0, sir. Sir, kernel T will be have, sir. Uh,
this has rank 2, na? Also one can write 300. Yeah, I think I got it. Here we have 3 eigenvector corresponding to V, B. Why 3 eigenvector? If we have distinct eigenvector, you know the geometric multiplication of 0 is 0, 2, then it will be rank is will be 1, right?
yes, sir.
Right, but that is true. Why? As
Sir, because sir, geometric multiplicity is strictly less than algebraic multiplicity, sir.
yes, but I just want to say geometric multiplicity of 0 is 2, then the Jordan canonical form will be like this way, right?
But sir, why GM is 2, sir? This is the
That is
question.
what I am just going to say. As A has distinct eigenvalue in C, here no one is restricting to me that on R, right? Real numbers, determinant of A. Okay, let's go to complex number, because rank is something always there. As A has rank 3, and diagonalizable over C, then it has 3 distinct, I have to there is an way, we have to do it by calculating the matrix, but I just want to go some other way. Okay, again 3 distinct eigenvector over C. Okay, let's take, let V1, V2, V3, these 3 are eigenvector. Okay, then no, not that technique will not. Okay, I think there is only one. Let's do it, that let's add those things. I have to find those matrix. I think that will not work, because A square eigenvalue will be
Sir, sir, can we not write the possible, sir, Jordan canonical form as sir B, sir?
yeah, that is what I'm just trying to say. For example, we have A have three eigenvalue, right? 1 W square, right? Corresponding to each eigenvalue there is a vector V1, V2, V3. Now corresponding to this eigenvalue, it has the B was something like A plus A square plus A cube. We know A cube is identity, that is not a problem. So now
Yes.
B V1 is equals to A plus A square plus A cube whole V1. We know this V1, V2, V3 are distinct, right? So we know, yes, there it is, we can get here. I am correct, I was correct then. A V1 is equals to V1, because that is corresponding to 1, plus A V1, A square V1, that means that will again V1, right?
V1,
Plus
yes.
that is V1 because A3 is identity, but again you can do the 3 things, 3 V1. So there is a 3 is the eigenvalue. So v1 is the eigenvector corresponding to eigenvalue 3, right?
Yes,
Now
sir.
let's
That
get,
we already got, sir. 3 is, sir. But the V1 is eigenvector for V also, sir.
that is what I am saying. v1 is eigenvector for 3. So now again b of v2, that is equals to a plus a square plus a cube whole into v1, that is equals to first is as w v1
V2, sir.
plus w
V2.
square, sorry, w v2 plus w cube v2, that means this is 0 dot v2, right? So v2 is an eigenvector corresponding to 0. v2
Hmm.
is an eigenvector of b. Now I think you can see it will be corresponding to 0, right?
Okay, sir. So GM will be 0, 2, sir. Of
Similarly,
0.
yeah, similarly you can do the same thing for v3, right? Similarly you can do, right?
Yes.
Similarly v3 equals to 0 dot v3, but v3 and v2 are linearly independent, because they are initially linearly independent, because they are eigenvector corresponding to different eigenvalue, right? They are independent, right?
Sir, I
That
have a
implies,
question, sir.
huh?
Sir, if A is, sir, diagonalizable, sir, then can we say that B is, sir, also diagonalizable, sir? If the relation is in some, sir, specific way, sir, like, sir, B is equal to
Yes,
A plus
that's
A.
true. That is always diagonalizable. That's true. If the a is in terms of polynomial, then you can say, because diagonal entries will polynomial. I mean, you suppose you have the diagonal. For example, you have diagonal matrix, right? Something a b c. This is the diagonal matrix. So square it. It will have here. Cube it. It will have here. Now add those things. It diagonally, all other entries are non-zero, right?
So, sir, if it is diagonalizable, then sir,
Right,
its
right, right.
polynomial
Polynomial.
will.
Yeah, unless it is not zero polynomial or something, right? You should not take the polynomial is zero or something. Yeah, only zero
So,
is
sir,
the.
so its sir, minimal polynomial will contain, sir, the linear factors, sir, distinct linear factors.
Hmm.
So
Hmm.
we will
Hmm.
get, sir, x into x minus one, three types, sir,
Hmm. Hmm.
kind of minimal polynomial. Then, sir,
Ye-
we can talk about this JC form of the, sir.
Yes, yes, yes.
P.
I think you can go. I mean, character is polynomial is there. You can go along line. There is no problem. I think most of the thing will go. But here it will be rank is 3. So rank B is, sorry, rank is 2. Rank is 2. Now rank is 2, right? Because you know the matrix representation will be 1 0 0, right?
Rank is one, sir.
So
So
rank is
rank
1,
is one, na, sir.
sorry, yeah. Rank is 1. So third is false, fourth is correct, right? Why this is happening is clear, na? Or should I say something more? Because you know that B
So,
will be, yeah,
sir, if A is diagonalizable, then P of A is also diagonalizable.
right,
This is always true.
yeah. Suppose I have D into P, right? So let's make it A square. What it will be? P inverse dp, P inverse dp. That will be P inverse d square p. That means you can take any power n, that will come at as an n, right? So that means if I take f is a polynomial, will be P inverse f of d into p. But you know, if d is the diagonal, d is something like diagonal a1 all the way an, then f of d for a polynomial, that will be diagonal f of a1 all the way f of an, right? So therefore that will be like p inverse, I mean this diagonal matrix diagonalizable, right? P, like this way. So always it is diagonalizable, because we are can keep a diagonal matrix, but the rank can change, because if a1 can be 0, that is what the problem. Okay. So but rank can change, but eigenvalue will be there. Eigenvalue also can change, but eigenvector will be keep, I mean corresponding eigenvector will keep fixed. So clear, right? So I have to go to the my problem now. My problem means the official assignment problem. Is it clear now? If it is not clear, you can ask me. Otherwise, I am going to the. I think we have done those things in last class. Oh, maybe I have not. just 1 minute. Okay, just 1 minute.
Sir, your screen is not visible,
No,
sir.
no, no, I just stopped sharing just because I that those problem. Now I will do problem from the from those which are I supposed to do.
Oops.
Yeah, that I have to do little bit in at least. So this is the first problem. So I'll obviously try to do as quick as it is because this problem is done. So this problem is done in the main course content, but let's do it again. Okay, I have
Oops.
to go. Let's more than around 20 minutes, 15 to 20 minutes I will go because of the lack
Oops.
of the things. Let V be an inner product space of polynomials over the field R satisfying these two conditions. I mean V is equals to polynomials. F is polynomial over R, that is in general written as Rx, such that f of 0 is equals to f of 1 equals to 0. Okay, equal to the standard inner product. Okay, no, not standard inner product. This is standard maybe, but that depends on the where it is defined. Real value. So this is like this. Let T from V to V is the real linear operator defined by T of fx equals to f double dash dash. Then the operator T is unitary. So T of f at x is equals to f double dash x. This is the thing. So therefore what we can say here is that then the operator T is unitary.
Sir, unitary and self-adjoint are same, sir, na?
Yes.
Sir, unitary and self-adjoints are same, sir.
No. If it is unitary, then it is adjoint. Self-adjoint is the same with inverse. No, sorry. Unitary and self-adjoint is obviously not same. This is something absurd. No, unitary is that
Is there
operator.
any relation?
Yeah, there is relation. Unitary and that operator is something this operator. If operator satisfies this, then this is called unitary operator. Self-adjoint
Yes,
means
sir.
it is same with its adjoint.
Hmm.
So if an operator is unitary operator, then it is invertible and its inverse is the adjoint of this. Along with if it is self-adjoint, then U equals to U inverse. That means U is idempotent.
Oops.
Okay, so this is not obviously these two things are not that much connected. So T be the linear operator given by T of fx equals to f double dash dash. Then the operator T is unitary. I am not able to go what is called matrix representation because here the space is infinite dimensional. So whether T star is equals to, so let's try to find what is the adjoint. That is the first place. So now T of fg, for example, this is equals to f double dash x or f double dash with inner product with g, inner product with g, and that is equals to 0 to 1 f double dash t gt dt, right? Now I have to go f inner product maybe I'm doing something td inner product space over the. Okay, I have to do the partial integration. Now 0 to 1 f double dash 0 to remove this range, 0 not range, f double dash t gt dt, what is the partial integration? U v dx is equals to u integration v dx minus integration du dx integration v dx dx. I think this is the correct one, right? U
So this is unitary, sir.
huh?
Unitary operator, sir. Option 1 is correct.
Option is correct, maybe, but I'm just trying to do it. Integration u vx partial differential is u integration v dx, so I have to take f double dash is the thing, so gt integration f double dash, so f dash t
Minus.
this is dx minus du dx, that g dash t into f dash t dt. This is the thing, right? So now if we do again gt f dash t minus minus, it will be first of all g dash t f, yes,
Yes, sir. FT. So first thing will be 0, sir.
now I have to replace 0 1, then it will be 0, right?
Yes, sir.
Yeah, but I'm just first calculating the things. So it will be g double dash t 0 to 1 is there, but okay, ft dt, this is the thing. So now if we replace 0 to 1, so 0 to 1 f double dash t gt dt, that will be g t
So,
f dash
so
t.
integral g double dash t ft dt, sir.
Yeah, last one will be there, that is the way it is constructed.
Yes.
Integration 0 to 1 g double dash t ft dt, right? So therefore obviously as f g of 0 1, as I am writing as g of 0 is equals to g of 1 equals to 0, and f of 0 equals to f of 1 equals to 0. So therefore first two term is 0, so this will be 0 to 1 g double dash t ft dt. So therefore what we are getting here is that integration inner product with f with the derivative of g, right? So that implies d star is
T
equals
of
to
g,
g.
sir. T of g, sir.
Yes, d of g.
No, sir. T of g, sir.
Oh, sorry, t of g, not okay. Operator is t, right? Sorry, I was. This is differential, double differential, not differential. T of g. So that implies that t equals to t star. That says that self adjoint. Okay, I have to. Just a minute.
Yes, sir. Correct.
Yeah, this is correct, right?
Yes, sir.
Okay, so what are the option is here? Then the adjoint of t does not exist, that's false. The operator t self adjoint, that's true. T plus t star equals to 0, that will be false. That is clear, right? Because t is self adjoint, so t star 0 means 2t equals to 0, but 2t is not 0. I mean that means equivalent to saying that t is 0. That is not true. This is also false. So whether t is unitary or not, that depends. That will also be not there, because t is unitary if and only if t star t equals to t star is equals to identity, but t star t is equals to t square. So t square of f means 4 times derivative, but that is not always 0, right? That is not identity, right?
Correct.
So therefore, t is self adjoint. Yeah. So one can check that option. All other options will be correct. I will just. So one can check that. One can check that. Yeah. One can check that. Except C, all other option is incorrect. Options are incorrect. Okay, so let's go to second problem. Yeah, this may be little good problem. So this is the problem. What it says, let u be the unitary operator and the super subscript represents the adjoint operator, then which of the following statement is correct? First option, that u is invertible. Okay, u the unitary operator, this is directly it is saying something. Okay, u be unitary operator. Okay, u is unitary operator, right?
Yes,
Unitary
sir. First
operator.
correct.
So by definition u star is equals to,
Second is also correct, sir.
yeah, I hope so, by
Third is also correct, sir.
Definition:
Fourth one is correct.
u star equals to identity equals to u star. So that implies u is invertible. That says option A is correct, right? And u alpha, option B, for option B, u alpha beta is equals to alpha u inverse beta. That implies alpha u star beta is equals to alpha. Oh, this is true or not? Sorry, this is true or not? That is true, obviously true. That is imply
Yes.
u star beta. But you know, from here one can say u star is equals to u inverse. So u inverse beta. Therefore this is also correct. This is also correct. Third option is also correct, because
Yes.
u alpha, that is the definition of the,
It is product preserving,
yeah.
sir.
So alpha, this is the definition of the unitary actually. So alpha beta, because in u star u is identity, this is equals to identity. So therefore this is also correct. What is the last option? That is not necessarily false. One can create some example. Let's take
U I. U is equal to I.
u is equal to, you can take u equals to identity, I think, right? And alpha is any vector, right?
I. Yes.
Yes, u
I,
equals to
sir.
identity. U equals to identity. Take u equals to identity. Take u equals to identity, and alpha is something for which the non-zero, something like this, identity 2, this is non-zero. Then mod of alpha square is equals to 4. Yeah, 4. So that means mod of alpha is equals to, norm of alpha is equals to 2. So norm of u alpha square, that is equals to 4 plus alpha square, plus norm of alpha square, that is equals to 4 plus 4, that is equals to 8. But that is not equals to 4, right? And that is equals to u alpha, which is equals to norm of u alpha, that is 2, and norm of alpha 4, right? Norm of u alpha, norm of alpha is 4. So therefore this is not true. Yeah. So let's go to another problem. It is necessary sufficient condition, this is intermittent. This is something loaded work, so let's do it. So what it says, the necessary and sufficient condition that the matrix A is equals to A, B, C, D, this is unitary matrix. So what is the A star? We know A star is equals to
A conjugate.
yes, a conjugate, that means A bar, B bar,
B bar.
C bar, D bar,
B
right?
bar.
So A star A is equals to A bar, C bar, B bar, D bar with A, B, C, D. That will be mod of A square plus mod of C square, and the diagonal is mod of B square plus mod of D square, and cross diagonal will be A bar B plus C bar D, and here will be the B bar A plus D bar C. This is the thing, right? And this is equals to 1 0 0 1. That implies mod of A square plus mod of C square is equals to 1, mod of B square plus mod of D square is equals to 1, and A bar B plus C bar D is equals to 0. So these are the options. AC minus BD, where it is getting. A square plus C square is 0, I think, but it is, if we write this way, A star, still it is getting mod of A square, mod of B square. Oh, got, sorry, I have to do another around. A star is equals to, then I may get A bar, C bar, B bar, D bar, that is equals to mod of A square plus mod of B square. This will be mod of C square plus mod of D square, and This will be AC bar plus BD bar. This will be A bar C plus B bar D, and this is equals to 1001. So what we will get? We will get
So it
1
will be
over.
same, na, sir. Because
No,
it
no,
is
no, no.
given.
There is two different thing. A bar C plus B bar D is equals to 0. But why this minus is here? What is the correct option here?
Sir, option C is correct.
Option C is correct. Okay, this is correct. This is
Yes.
okay. Okay, we have to extract from here. I think then that is that we have to take C is
Sir,
equals to cos theta, or
sir, take find it, sir, in terms of sir determinant, sir. If you sir find determinant of A star, it will be sir 1.
yes, that's true.
And determinant A star is equal to determinant A into determinant A star, sir.
Yes, then we'll get those things.
And determinant A star is equal to determinant A conjugate, sir.
Bar you are saying? Yeah, it will be. I think it will be.
Yes, sir. So basically, sir, we are getting the determinant A into determinant A conjugate is equal to 1, sir.
Yes, that's true.
So, sir, determinant A should be in the form of e power I theta.
Determinant A will be in the form of e to the power I theta. But still no. I think we can do from here also. Let's. I mean, we have to take C is equals to that way. I think. Mm, how can I can say A bar C is equals to B bar D, as this is diagonal. Okay, I will not do this.
Sir, we have to introduce, sir, e to the power I theta, na, sir.
Yeah, that way is there, but I have to take, yeah, that another way is there. We have to take C is equals to some C1 e to the power I theta plus C2 e to the power minus I theta. That way one can take, but that is very long way. So one can take here is the something like C equals to, what it is saying, that C equals to minus B bar e to the power I theta, and D is equals to, okay, I think one can do this way also. There is many way, but right now what is the correct way will be the shortest way, that I am not able to understand. A bar B AC minus BD bar, that is not correct. C is equals to this will be the correct option, that's true. What are the way you are saying that go via through determinant?
Yes, sir. Yes, sir.
Determinant will be AD minus BC, and this determinant will be again AD minus BC. So what is the problem?
Conjugate, sir. There will be
Conjugate of that. That's
conjugate.
true. That's true.
Yes, sir. And because this is sir 1, sir, so determinant will
Product,
be
yeah.
sir 1.
So that means mod of AD minus BC equals to 0. So that I have to add, you are saying. So also, as determinant of A is equals to AD minus BC, and determinant of A star is equals to AD minus BC bar, and also determinant of A star is equals to mod of AD minus BC square, that we know. Anything else from here? There is a way one can do, that is taking e to the power I theta.
This will imply, sir, modulus of determinant A square is 1, sir.
Yeah, that's true. Then AD
This will,
minus BC is equals to 1, mod of this equals to 1. So AD minus BC is equals to taking e to the power I theta.
yes.
But where I will replace?
Now use, sir, the relation, sir. A bar C plus B bar D is equal to 0, sir.
but here it is AD minus BC. There is A bar C plus B bar D.
So sir, first write it, sir. Then A bar C is equal to minus B bar D, sir.
That's true.
Now assume that if A and B, sir, there will be two cases, sir. If A and B are sir non-zero, then we can divide, sir,
That
by.
is that what I can see, but
Then you can introduce, sir,
one
determinant.
obviously A and D can't be simultaneously 0. That's true.
Yes, sir.
A and
Then
D
now
can't
you
be
can divide.
simultaneously 0. Either A is non-zero or D is non-zero. At least one of both
Yes, sir.
of them are. I think both of them are non-zero. This is unitary matrix. I think. No. Both of them are non-zero. That I can't say.
Yes, sir. Both are non-zero because modulus A square plus modulus B square is one, na, sir.
Oh
Both
oh
are
oh
zero.
oh 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 oh. Oh, B
Yes,
square.
sir.
No, mod of A square plus mod of B square is 0. So 1. So therefore at least one of them is non-zero. So I have to replace them, right? So let's take
No,
let
sir. First,
let A
sir.
not
First,
equals to 0.
uh,
Then what we'll get, or let's take B. Okay, let A not equals to 0. Then what I will get, that C is equals to minus B bar by A bar D. So if I replace this one here, right, AD minus B into plus C is equals to B bar by A bar D is equals to e to the power I theta, right? So what I get, mod of B square plus got it plus mod of A square whole to the power D in equals to e to the power I theta A bar, right? And this is equals to 1, we know, so D is equals to, yeah, thanks. Similarly one can obtain, that's true. Similarly one can obtain C is equals to minus B theta. So therefore similarly, there is no similarly here, you have to just replace this. So C is equals to minus B bar e to the power I theta. Yeah, thanks. This is the correct option. So
yes.
I think okay, let's do one more problem and then I'll stop. I'll take easy now. Then which of this is the easy one, so let's do this one. So given a linear operator T on a finite dimensional linear product space V, T is self-adjoint and unitary. So therefore what we have, that T star T is equals to identity equals to T star, and T is self-adjoint, that means T star equals to T. In which of the following statement is or are correct? Okay, following statement is or are correct.
First is correct, sir. Second is not correct. Third is correct. Fourth is correct.
T is diagonalizable, that's true, but from where one will say diagonalizable is true.
So there is a theorem, sir.
The normal operator is not is diagonalizable, right? Self-adjoint operator is diagonalizable. That's true,
Yes.
but unitary operator is self-adjoint, so that will be diagonalizable. But yeah, I got the point. So but those things I am not able to use now, na? T square equals to identity as T star is equals to T. Therefore x square minus 1 is minimal polynomial.
Involuntary operator.
Minimal polynomial, right? So that is completely factorized. X minus 1, x plus 1, that implies that T is diagonalizable.
Yes, sir.
So first one is correct then. But that is also saying that T to the power m equals to identity for all natural number m.
Not
that
true.
is false. So the T,
Yes.
the eigenvectors of T form an orthonormal basis of V. That's true because T is diagonalizable. Eigenvectors of T are, no, they are orthonormal says, but we know that they are eigenvectors are there, but why they will be orthonormal? Because of the unitary. Okay, let eigenvectors are alpha 1, alpha 2 all the way alpha n. Maybe I have taken the n vector, so I have to say alpha 1 alpha j is equals to something, right? So either they correspond to 1 or correspond to 0, minus 1. So let's corresponding to alpha is corresponding to 1. So t of alpha I comma alpha j, right? Let alpha is eigen value corresponding to 1, right? So therefore what it will have, and alpha j, there is 4 case actually.
So
Yes,
there is t of alpha j, na sir?
yes,
Alpha I
yes, yes,
alpha.
that is also can be written, but alpha j, if alpha j is corresponding to minus 1, then I have to take minus 1 minus left hand side.
Yes, sir. What, sir?
No, t is self adjoint, I don't need to go there. Okay, alpha j. So what we will have, alpha I comma t alpha j, right? Because t is self adjoint. I have to show that alpha I alpha j is equals to 0. That means if I can show that this is minus, then it will be.
Sir, self-adjoint means
Hmm? No, this is not true. Then eigenvectors should form
how
an orthonormal
can
basis.
be true?
Eigenvectors will be orthonormal basis. Yeah, orthonormal is correct. Orthonormal is correct. Orthonormal is correct. Why
Sir,
orthonormal is correct? Okay.
every normal operator can be, sir, unitarily, sir,
No.
diagonalizable, sir.
Unitarily equivalent is not the fact. Problem is that I have to say that norm of alpha is equals to 1, right? To show. Then note that norm of alpha I square is equals to inner product of alpha I. Therefore this is alpha I can be taken t star alpha t star this side, t self adjoint, that is identity alpha I. What I can say more than this, alpha I t alpha I. I think this is the not on the option here. No, this is option. Orthonormal. Why that is orthonormal? T is isomorphism, that is for sure. T is an isomorphism, that is for sure, because T is unitary, so that is isomorphism, there is no problem. Eigenvectors of T form an orthonormal basis. Yeah, that can be done, but there is some process which I don't want to involve here. Eigenvectors correspond to distinct eigenvalue are orthogonal to each other, that's true, there is no problem. That is first thing. Second thing is that eigenvectors of T form an orthonormal basis. Any eigenvectors will be orthonormal basis. I have eigenvector.
Sir, if we write, sir, alpha inner product of alpha is equal to t of alpha I inner product t alpha, sir. And since alpha is, sir, eigenvector,
Yeah, this one. Then
sir, alpha is an eigenvector, so t of alpha I can be written as some lambda I alpha I, sir.
but
Inner,
eigenvectors are only 1 and minus 1, right?
sir, then
Either it will be corresponding to 1 or minus 1. So there is,
yes, sir, we get equal t, sir.
yeah, for
Nothing.
example I just taking 1 0 0 minus 1. If V is equals to, this is self adjoint, this is everything, right? This one with some eigenvector, if I want to get an eigenvector, what will be the eigenvector? Let's take 2 0. What is this? This is 2. I think this is wrong option, that's why I was confused. 1 0 2 2 and next one is the 0, right? This is the thing. So therefore this is the matrix which is satisfying all other condition, right? This is self adjoint, t star t is equals to identity, unitary operator, everything is there, and this is making 1 to 0, but this is not an eigenvector, this is not orthonormal, not norm 1, right? So this is, so in that way this is not correct. Got it, na? Got it what I just want to say?
Sir, but Sir, the normal operator can be, sir, ortho,
No, no, they
sir,
can
or
have. They can have the eigenvectors of T form an orthonormal basis. That is not necessarily true. No? They can have. They obviously will have because that will there. There exists an orthonormal basis with respect to it that will be diagonal. But but
every eigenvector will not form the orthonormal
right. For
basis.
example, you can take 1 0 0 minus 1. This is the operator T
Hmm.
over complex field. T is self adjoint. You know the adjoint of this is again this is because diagonal matrix is this.
Hmm.
And if you multiply with this, then what you will have, this will have g1 0 0 1, so this is unitary as well. Okay, so it has 1 and minus 1, these two eigenvector, that is clear. Eigenvalue, this is clear. So let's multiply 2 0, what it will have, this will be first will be 2 and second will be 0, right? So
Hmm.
but 2 0 is not an ortho element of orthonormal basis because this is neither orthogonal is possible.
Sir, but 2 0 is not a, sir, sir, eigenvector, na, sir.
2 0 is eigenvector here na.
Acha, corresponding to 1, sir. Okay,
Yes,
sir. Hmm.
so this is somehow a little mistake, orthonormal it will not be. T the eigen T will have a space of orthonormal basis consisting eigenvectors, that's true, but that is something little different. So I will stop here. I got very late, and thanks. If I hope there is any any other doubt, right?
No, sir.
Okay,
Thank you,
so
sir,
I'll
for
stop
your
here.
time.
I'll
Okay,
for the next class. Okay, thanks.
okay, okay. Thank you.